Hello and welcome to this recorded e-learning on Basic HDL Coding Techniques Part 1. My name is Frank Nelson. I'll be your instructor for this module. This module introduces the primary HDL coding techniques that most FPGA designers use for their design construction. This module introduces some of the primary concepts that impact the quality of results a designer will get when synthesizing for a Xilinx FPGA. This module also provides some detailed recommendations about creating effective HDL that will provide high speed and save FPGA resources. This module requires that the designer already know how to code with VHDL and/or Verilog. Many of the topics discussed include HDL code in either VHDL or Verilog language. We do not expect the user to know both languages, but most designers can create code as described in this module. After completing this module, you'll be able to specify FPGA resources that may need to be instantiated into your design. Identify some basic good guidelines that successful FPGA designers will use. Select a good HDL coding style that provides fast and efficient circuits as well. But the key thing is that many new customers are disappointed that they are going to have to instantiate some of the most popular FPGA resources into their design. This is now pretty much standard operating procedure in the FPGA industry. What I mean by that is that most customers are prepared to create highly optimized cores with the Xilinx core generator or the Xilinx architecture wizard utilities, and are then going to have to instantiate them into their HDL. Now, this flow allows users to work around limitations all synthesis tools have with regards to automatically inferring the best FPGA resources. The bottom line is that all the high-end synthesis tools available for FPGA industry usually do not allow inference of all the best FPGA resources. That is usually the latest and greatest, like the DSP slice and block RAM resources. Now, synthesis tools may allow some inference of these resources. There are plenty of exceptions, but usually only primary applications are inferable. For example, the block RAM resources are inferable for memories that only use a single block RAM, are not initialized, and don't use the output register functionality. So simply put, it is too difficult for synthesis vendors to keep up with all the possible configurations of a single FPGA resource and build the ability for the users to infer all that possible functionality. So in the end, since most customers want the high-end resources, the newest resources, and all the functionality, that requires them to instantiate. To aid customers in building a desired component of complete functionality, we recommend that users build their components with a core generator or architecture wizard. When I mention high-end synthesis tools, I'm referring to the most popular synthesis tools available for the FPGA industry, specifically Simplify and Xilinx's own XST. While this module is not about how to use those synthesis tools, it is important that users learn about proper use of their synthesis tool and their tool's limitations. Now, we provide some basic information about synthesis options in the Designing for Performance course, commonly called DFP. This module will discuss in detail proper HDL coding techniques for the most common and fundamental components designers make. To get optimum speed, device utilization, and minimal power, customers need to plan on targeting as much of the FPGA's dedicated hardware resources as possible. This means that users not only have to plan on instantiating the proper resources, but sometimes have to look for creative ways in which to use the dedicated resources. For example, most customers would think to build a FIFO with the block RAM, but most would not consider building a finite state machine with block RAM. Very often, customers choose a device that has some dedicated resources left over. So to get the most out of the FPGA, users have to very often pack the most into the FPGA, and in particular, those dedicated hardware resources they weren't using. Writing good HDL is of course important because it is used by synthesis tools to infer the most popular FPGA resources, that is, LUTs and registers. Since there is very often more than one way to code for effectively the same functionality, it is important to understand the differences between two different or more ways to code a function. This is compounded by the fact that often a poorly coded piece of logic creates a timing-critical path for a designer to resolve later on, and often designers waste a great deal of time resynthesizing and repeating a place and route solution, hoping to meet a timing objective. Another very common FPGA design practice is for a designer to pipeline a timing-critical path. Now, this is done by inferring extra registers on a long data path so a long net delay or multiple LUTs in series can be tolerated. If you are not familiar with pipelining, Don't worry, we'll talk a bit more about this later on. Finally, to improve the speed of the output netlist made by your synthesis tool, it is important that you take proper advantage of the synthesis options available to you provided by your synthesis tool. Now, we'll talk more about this in the Design for Performance course, as I mentioned earlier, but we wanted to mention some of our general recommendations for driving your synthesis tool here. This slide is trying to highlight some of the benefits of the dedicated hardware resources that exist in the newest FPGAs. The most useful of the dedicated hardware resources is the DSP slice and the block RAM resources. Besides using less power and saving primary FPGA resources, that is, LUTs and registers, using the dedicated resources makes it easier to estimate timing. This is because the architectural delays of the dedicated resources are known before place and route. Unlike data paths that may contain multiple LUTs and nets in series, data paths that use the dedicated resources do not require any programmable routing delays, except to route to and from the dedicated resource. Another reason to use the dedicated resources is that compared to soft implementations, now that means a LUT and a register implementation of the same component, but compared to that, the speed of the dedicated hardware is significantly faster than, shall we say, a soft implementation. So be sure to use as much of the dedicated hardware resources as your design needs, and if you think you may be running out of primary FPGA resources, consider implementing more of your design in leftover dedicated hardware resources. This slide describes the timing closure flow for Xilinx FPGAs. You may recall this slide from the Essentials of FPGA Design course. Timing closure is introduced in the Essentials of FPGA Design course, but is a primary topic in the Designing for Performance course, commonly called the DFP course. What I want to point out to you is that the most important efforts to improve design speed are recommended very early in the design flow, even before completing a single implementation of the design with the place and route tools. And this is where we make good coding decisions, and this explains why making good HDL code is critical and is most beneficial when good coding styles are used from the beginning of the design process. As I mentioned earlier, most designs will require at least some instantiation of dedicated hardware resources. This is because all synthesis tools have limitations on their ability to infer all of the FPGA resources. Now, this is especially common when the dedicated hardware has as much flexibility to be used in so many applications. So, for example, the DSP slice can be used for multipliers, large muxes, MAC functions, filters, ALUs, etc. So it's a very flexible component, and of course that can be challenging to infer all that functionality. While we recommend inference, if possible, when you instantiate components, try to place the instantiations in one location, usually at the top level of your design. This will make it easier to port your code to another device family or technology later on, while reusing as much of your generic HDL as possible. We also recommend using the core generator and, as I mentioned, the architecture wizard to create your optimized components. These utilities are a standard part of the ISE tools and, of course, are included with the toolkit. This is a short list of the most commonly inferred resources. For example, the shift register LUT is commonly used to build delay elements or pipeline stages. It is easily inferred, but with the limitation that the outputs cannot be reset and its contents cannot be initialized. So if a user were to code for a shift register with a reset, there is no way any synthesis tool could infer the SRL. There would also be no warning or error message sent by the synthesis tool, since the tool would think you wanted to build a shift register with your standard flip-flops. There would be no error in that. Likewise, the implementation tools would not give a warning or error message, since the netlist made by the synthesis tool would reference flip-flops. And as we know, there's nothing wrong with that. You should also note that even if you were to build an appropriate shift register component, your synthesis tool may still require you to place an appropriate attribute in your HDL that will tell it to map to the SRL primitive. So one of the most helpful skills a designer can have is to have enough experience with their synthesis tool to know the appropriate attributes and its appropriate coding style limitations for that synthesis tool. One of the best ways to determine how to infer a resource is to go to support.xilinx.com and open the XST user guide. Now this is also associated from the ISC software. You can get it there from the help menu as well. And then do a search for SRL coding techniques, and you'll find examples of how to infer the shift register LET. Now this user guide provides numerous examples of a wide range of dedicated architecture resources in the FPGA and shows you how to infer the best FPGA resources. So be sure and check out the XST user guide. Now most designers are instantiating memory resources, I/O standards, including SerDes functionality, and clocking resources on every design. That is because there is just so much flexibility with this FPGA architectures that the synthesis tools just can't build a tool that will infer all the possible configurations that a customer might use. So you're probably better off planning to instantiate these resources from the beginning. As I mentioned earlier, we suggest that you keep your instantiated components in one location. Now, most designers place the Xilinx specific instantiations at the top, or one layer down or one level down, but never more than that. This makes it easy for the user to locate and maintain the design and port your code to another device family or technology later if necessary. We also recommend keeping your pin assignments and pin attributes in your design's UCF files so all the Xilinx specific constraints are removed from the HDL. This makes your code more generic. Another instantiation option a designer has is to use the VHDL configuration statements or put wrappers around each instantiation. Now this will maintain the design hierarchy and still make it easy to swap instantiations if your design migrates to another architecture. Xilinx recommends that hierarchical optimization. Now that is a standard synthesis option that allows users to optimize combinatorial logic across a hierarchical boundary. Now we recommend that this hierarchical optimization be turned off. This is because synthesis tools will change node names and change the logic optimization on nodes that users will often want to simulate, probe, debug, or analyze in some way. Allowing this optimization will sometimes make debugging nodes on a hierarchical boundary much more difficult. So in general, we tell our customers to leave this optimization across hierarchical boundaries off and only use it later as a final last-ditch effort to gain time and closure. Fortunately, most customers don't get this desperate, but we like to mention the proper use of your synthesis tool here so that you have the ability to debug and simulate nodes later. Now, all synthesis tools will default to not allowing optimization across any boundaries. However, if you choose to enable this optimization, only enable it across the boundary associated with your timing critical path and never allow it to be used globally. Maintaining your design's hierarchical boundaries yields numerous benefits. As I mentioned a moment ago, it makes it easier to locate nodes when you are simulating, probing with chipscope, for example, or simply reading a synthesis or timing report. However, what many customers don't realize is that it also enables floor planning and use of the incremental design flow. Incremental design allows users to maintain the place and route solution found for part of the design and only repeat place and route on components that failed to meet timing or have changed logically. Note that most experienced designers know that for optimum speed they need to make sure that critical timing hierarchical boundaries have registered outputs. This is a pretty standard way for users to tolerate a high fanout net that a component might be making, or if they know the placement of the destination logic might be far away. But commonly when a designer makes a purely combinatorial piece of logic, adding a register can easily be accomplished by converting the component to a registered component. If the component already has its outputs registers, then optimizing across a hierarchical boundary will have no effect since logic optimization won't remove a register in that case. You may recall that I mentioned it's important to be aware of what your synthesizer will generate depending on how you code a piece of logic. The first component we're going to look at are muxes. If you build a mux with if-then statements, synthesis tools will almost invariably build logic into priority encoders. Now likewise, if you build it with a case statement, the synthesis tool does not give any signal a priority. So if you build a mux with if-then statements, note that the timing critical signal, that is, the signal on the first if statement, ends up in the last logic stage. This signal will have to go through only one logic level and have the shortest delay. This is perfect for the case when you need one of the inputs to be faster than the other inputs. You may have also heard about that unintended latches or complex clock-enabled equations can be synthesized when your if-then or case statements do not cover all possible conditions. Now, fortunately, synthesis tools warn users when they are building latches, but they do not warn when the long clock-enabled equations are being built. That is why it is important that you verify for yourself what is being synthesized by your HDL. To do this, the best tools provide schematic viewers that show when this is happening. So this example shows you that the if-then statement construction of a mux builds LUTs in series. Now, it is very important that you understand that having these LUTs in series produces long delay paths. Just look at the do_e input. Its path to the output requires 4 LUTs and 3 net delays to be traveled before the output would be accurate. So this and the do_c paths are the longest and will be the most timing critical paths through this component. Conversely, the critical_sig path will only have to travel through 1 LUT. This is, of course, much faster. The component's construction was all inferred by the synthesis tool when we coded the mux with if-then statements. Note that the order of the inputs to the if-then statements, the most timing critical is listed first, followed by each of the lesser critical signals, and ending with the least critical inputs in the statement. Now, if you build with nested if-then statements, be sure and watch your timing on your inputs because the LUTs can cascade easily. Always be sure in this case to put the timing critical signals first in your HDL. However, the best solution is to build the component with a case statement as much as possible. Case statements do not build with LUTs in series and tend to build the LUTs in parallel, which is dramatically reducing the number of logic levels. If the last example was constructed with 4 input LUTs, it would require only 2 logic levels. Recall that the function had 9 inputs, which would require 2 LUTs in series and a total of 3 LUTs. So see if you can make that work and replicate what we expected and how the difference would come by using a case statement. Case statements are almost always the way to go when muxing logic. However, be sure to define all outputs in all branches. Otherwise, this will produce a latch and a warning message. To do this, we recommend using a default statement before the case statement. Case statements used in a register processor always statement can produce a long clock-enabled equation. So likewise, we recommend using a default statement before a registered case statement. Some other recommendations include registering the select inputs to your case statement. This is especially helpful if there are a large number of inputs to the multiplexer, since this component might require several logic levels to be constructed. Recall that the more logic levels in series, the more net delays in series, and this quickly adds up to a lot of delay. To work around this, registering the inputs to the select lines will effectively pipeline the large combinatorial path from the LUTs used to generate the select inputs. Another creative solution to this same problem is to use one-hot encoded select inputs. One-hot encoding reduces the complexity of the logic generated by having only one signal represent the input. So rather than having the 3 select lines that require decoding 8 possible combinations, we could use 8 select lines where only 1 bit is used to determine which input is selected. Lastly, test out building a mux using a case statement with your synthesis tool. Usually, synthesis tools will put the last signal listed in the case statement in the last level of logic, meaning that it will get the shortest path. This example shows a 6-to-1 multiplexer with binary coded inputs. Notice that a default value has been defined for the remaining possible combinations of select line values. This makes the implementation much smaller. XST used not only LUTs for this design's construction, but also took advantage of the dedicated muxes included with each slice. These muxes allow larger multiplexers to run faster and save LUTs. In this case, the result used fewer LUTs and got better performance by having the dedicated muxes available. This design also inferred a register on the data out signal. This effectively added a pipeline stage. Recall that this is one of the best ways to improve system performance in an FPGA. If this did not have a registered output, a critical path could evolve through this mux. It's usually best to always try to build the outputs of the lower leaf level boundaries with an output register. Now we have rebuilt this component, but with the select lines one-hot encoded, so you can get an idea what we're talking about. Now this mux used more LUTs than the binary encoded version, but had a shorter timing critical path. This is typical using one-hot encoding techniques. However, if this mux were much larger, it would have been much faster than the binary encoded version, but would have also been much larger than the binary encoded version. That is, it would use more LUTs. That is because there are now 12 inputs to decode, not 9 inputs, as in the previous example. Some other basic performance tips include avoiding high-level constructs like for loops. Sometimes synthesis tools don't produce the most efficient result, so be sure and test these components with your synthesis tool. Another commonly known coding style is to group arithmetic and logical operators, such as we see here. This guides the synthesis tool to map B and C to one LUT and map D and E to another LUT. This is the most efficient mapping. Recall that the carry logic resource will program each LUT to do the addition of 2 bits plus the carry input. This is also important for logical functions. Finally, use synchronous resets whenever possible. Not only is this good for circuit reliability in all FPGAs, but it enables efficient mapping to the FPGA architecture. Synchronous design works best for numerous reasons, most of which we explain in more detail in a later module, specifically the Synchronous Design module as part of the Essentials course. The most significant reason is that your design can fail if it maps to a different speed grade, device family, or product. This leads to a great deal of insecurity about the reliability of the design. It also wastes time, not just timing, but your productivity when you try to debug a design at a much later date. Synchronous designs have as few clocks as possible, use synchronous resets, and have no gated clocks. Now, if a customer insists on having an asynchronous reset, I usually tell them that their circuit should behave okay as long as the reset is global, but I never allow a local asynchronous reset in a design. For more information on synchronous design practices, check out the Synchronous Design module as I mentioned in the Essentials of FPGA Design course. As I mentioned a moment ago, using synchronous sets and resets is one of the elements of proper synchronous design. In these examples, you can see that we have inferred D flip-flops with synchronous and asynchronous sets and resets. It is important to remember that for a control signal to be synchronous, it must be contained within the always block and not be listed in the sensitivity list. So example 1 is just a simple D flip-flop. Example 2 now has an asynchronous preset inferred. This is accomplished by placing the preset in the sensitivity list. Example 3 has a D flip-flop with an asynchronous reset for the same reason as example 2. The reset has been placed in the sensitivity list, so the flip-flop must have the behavior that if the reset is asserted, it will reset, regardless of the rising edge of the clock. Now example 4 shows a proper register inference. The flip-flop has a synchronous reset by not including the reset signal in the sensitivity list. In other words, the reset is only checked when the rising edge of the clock has been detected. In examples 2 and 3, the asynchronous control signal can be asserted regardless of the rising edge of the clock, and that's not good. Clock enables are used in synchronous design. They should always be used instead of gating a clock. As you know, gating a clock signal and then driving it to a clock port on a flip-flop can glitch in any FPGA. To synchronize the clock, just drive the derived clock signal to the clock enable port. In these examples, we see the clock enable as a simple 1-bit signal, but it could be whatever derived signal you want it to be. The key is that the enable check is a nested if-then statement, usually right after the clock signal. For clarification, we mentioned earlier that nested if-then statements are not recommended. That was only in the case of building purely combinatorial logic. In this case, it is a register process that is not inferring combinatorial logic. You should also note that if you infer an asynchronous reset or preset, or even gate a clock signal in your design, your synthesis tool will not send a warning or an error message. It is left up to you to avoid making a big mistake in just that case. Now, let's take a few minutes and review some of the design practices that we have provided for you in this REL. Now, let's wrap up this module with a summary. First of all, use as much of the dedicated hardware resources as possible to ensure optimum speed and device utilization. And what we're talking about here is try to target as much of the dedicated hardware so it will save you using lookup tables and registers in your standard array logic. Plan on instantiating clocking and memory resources. As we mentioned, these are very commonly instantiated by most customers. It is possible to infer the primary functionality for the rote, simple implementations of the clocking and the memory resources. But again, the architecture wizard and core generator are there for that purpose, to allow you to instantiate those components easily. Try to use the core generator not only for the clocking and the memory resources, but also other dedicated FPGA features like the DSP slice and the FIFO logic resources. Also, maintain your design hierarchy to make debugging, simulation, and report generation easier. Continuing on with the summary, case and if-then statements produce different types of muxes. As we described, case statements tend to build logic in parallel, while if-then statements tend to build priority encoders. The priority encoders tend to often make timing critical paths later on in a design. So in general, build with a case statement if you can. Avoid nested case and nested if-then statements. Again, for the same reason. It tends to build logic in series rather than in parallel, and it tends to slow the performance down. You should always build a synchronous design for your FPGA, not just for speed, but the key thing here is to save you time and make your design more productive. And we mentioned a couple key tips about following good synchronous design practices. Build with your clock enable and use synchronous sets and resets whenever possible. Never build asynchronous sets or resets. Lastly, inferring many types of flip-flops from your HDL code is possible. And as we mentioned, those synchronous sets and resets are preferred. The first recommendation is to always keep the next state logic and the outputs of the state machine in separate process or always blocks. When this happens, the largest and most complex finite state machines will yield better performance since resource sharing is prevented. Note that the state registers can be in the same process as the next state logic, but if your finite state machine is large, it might synthesize better if it is separated. Resource sharing often hurts the speed of the large finite state machine. That is because the complexity of finite state machines sometimes will create multiple levels of logic in an effort to reduce the finite state machine's size. So when it comes to synthesizing the state machine, turn resource sharing off. However, if your finite state machine is pretty small, it may not hurt for it to be on. Ideal finite state machines have inputs, outputs, and control enable signals. Inputs should only include input signals and state machine jumps. Outputs should only be output states, control signals, and enable signals. It is inefficient to build finite state machines with arithmetic logic, data paths, or combinatorial functions included within the finite state machine itself. When this happens, there is less logic to create timing critical paths. Remember that most designs that include finite state machines find timing critical paths that pass through the state machine itself. Careful consideration of the design of the finite state machine is not only good for speed, but also important for building a reliable FPGA design. This is because finite state machines often will expose glitches and ground bounce problems designers build into their FPGA design. Your finite state machine encoding is important for both size and speed of your design, especially if it is large and or complex. Most synthesis tools have commands to encode finite state machines when enumerated types are used. When synthesis tools make decisions like this, it is not always the best choice. I recommend building the machine and then resynthesizing for binary, one-hot encoding, and or gray encoding, and then compare the speed and the size of each of the synthesized state machines. After construction, this will take a little effort to test each encoding. One-hot encoding is thought to build the fastest finite state machine, but this is not always the case. It simply depends on the complexity, the number of inputs, and the number of states. Most synthesis tools will choose one-hot encoding based purely on the number of states. In fact, most will choose one-hot encoding when the state machine has between 8 and 16 states. You should also be sure that you register the outputs of the state machine. This is frequently necessary if you're building a large or complex state machine, since these usually infer extra levels of combinatorial logic. This is why state machines are frequently part of a design's timing critical path. So make sure, after you have separated out the next state logic from the finite state machine outputs, that you also make sure both processes have registered outputs. The benefits of controlling the encoding of your finite state machine are mainly size and speed, but it is interesting to note that years ago most FPGA customers came to be concerned about their encoding because of design reliability issues. That is, 10 plus years ago, many customers were just not used to employing synchronous design techniques in their FPGA design. This was mainly due to ASIC design conversion, but in the end their design had to be synchronous to operate. Still, many customers had problems with their designs operating, and this would usually show itself with the finite state machine glitching. This was because most designers used binary encoding, and when a design glitches, it would usually cause the binary encoded machine to expose the flaw. So they would call the hotline, explain the issue, and the application engineer would fix the problem by convincing the customer to go to one-hot encoding. One-hot encoding worked most often because only 2 bits switch at one time, while binary encoding can allow many bits to change at each time. Well, now that everyone designs synchronously, there are no benefits to going to using one-hot encoding for reliability anyway. In the end, one-hot encoding can give more speed, depending on the state machine, at the expense of having a larger size. Gray and Johnson encodings are a hybrid of the one-hot encoding. They're smaller than the one-hot encoding and are designed to have fewer bits transition at once, so they are more reliable. But this does not matter if your design is synchronous. So, which encoding is best? Well, it simply depends on the complexity, number of states, and the number of inputs to your state machine. The more inputs and states, the more LUTs will have to be cascaded in series, and the slower it may run, and the more likely you'll have to use one-hot encoding just to improve the speed. Bottom line, the more complex your state machine, the more you'll benefit by trying all 3 of these different encoding techniques and comparing the size and speed of each. Don't expect your synthesis tool to do that kind of work. It's just too much for you to expect. You'll have to try this and experiment yourself. Now this finite state machine is pretty basic. There are 4 states and 2 output signals, really small. So really choosing a encoding style here for such a small state machine wouldn't be worthwhile. It's just too tiny. Note how the outputs are not defined in the same always block. They have been placed into a separate always block in effect to simplify and allow pipelining of the design. Note the reset used. It is asynchronous. That's not a good idea. This example should remove the reset reference from the sensitivity list in order to make the design synchronous and assure it will operate properly. So there's 2 things to note here. Don't bother trying to encode your small state machine. Make sure you use a synchronous reset, and separate your outputs from your next state decode. This slide shows the rest of the finite state machine. This always block shows the next state logic as part of a large case statement. Note that it uses a default statement. This will reduce the size of the finite state machine and is critical. So make sure you use a default statement. Here we see a finite state machine encoded for binary by using the parameter statement. The parameter statement allows you to guide the synthesis tool to your chosen finite state machine encoding. This can not only include one-hot encoding gray, but also a custom encoding of a designer's choosing. It would be a simple task to re-encode it for one-hot encoding or gray encoding and then test it for speed and size. In fact, this is what most of our customers do when building a large and complex state machine. They'll synthesize it for different encoding and compare the results for speed and size. They will also simulate using binary because, well, of course, we all know what a binary pattern looks like. Then, after they've verified its functionality, they'll switch it to another encoding and resynthesize it to compare for size and speed. Now, just to show you how easily it can be done, now we have simply re-encoded the state machine for one-hot encoding. You probably already knew this, and you could have easily done it yourself. No big deal. But again, we're just trying to highlight how easy it is to change it by using the parameter statement. Now we're going to look at the same finite state machine, but coded in VHDL. So again, we see 4 states and 2 outputs. Nothing new here. On this slide, we see that the next state transitions are defined in a large case statement, with the finite state machine outputs also defined. This is not recommended since most finite state machines are larger than this one and more complex, and they would get better speed by separating out the outputs from the next state logic. You should also note that this finite state machine defines a default output value. This simplifies the logic generated and is a recommended practice. This is the synchronous portion of the finite state machine. Note that with this construction, the outputs are also registered. While this is perfect to register the outputs, in essence effectively pipelining an output stage, note that the reset signal is asynchronous. So not a good idea to build it asynchronously. You'll need to recode this to make it synchronous to assure it will operate. But again, adding the register stage rather than leaving it purely combinatorial is very good, as we'll learn more when we get into the pipelining discussion. On this slide, we have built a larger finite state machine and not defined its encoding. When synthesis tools see this, they usually encode it as binary if it has less than 8 states, and it will code it to one-hot encoding if it has less than 16 states, and gray if it has more than 16 states. It's also interesting to note that synthesis tools assign state values starting with the leftmost value in the list. So state 1 would be all zeros, state 2 would be 001, etc., etc., and then state 7 would be 110. Finally, we see an example of a one-hot encoded finite state machine. In VHDL, this is a little more intricate, as we can see. An easier way, if your synthesis tool will support it, is to use a one-hot encoding attribute to be placed on a user-defined type. If that is the case, use the unspecified encoding example from the previous slide, along with this synthesis option to make your one-hot encoding finite state machine. So this is an option. You have to go into Synthesis Tools GUI and select the encoding there. Pipelining is the adding of a register stage to shorten a lengthy delay path. In this example, we see a piece of combinatorial logic between 2 registers. Normally, designers are not trying to pipeline a path with just 2 LUTs, but most commonly, they are pipelining their longest paths or paths that have a long net delay. In this example, a register is added between 2 flops, and the path delay is decreased by almost 50%. The caveat to pipelining is that the designer has to balance the pipeline delay paths. In this example, the data path would be delayed by 1 clock cycle. So if there were other parallel data paths, they would have to be delayed by 1 clock cycle. Well, there are 3 primary situations in which customers pipeline the design. Most customers register all the signals going into and out of the FPGA. This is simply the fastest way to clock data into or out of the device, and of course is done within the IOB register resources. Another important practice to improve the speed of the design is to register the outputs of each lower leaf level output signal. This assures that any long net delay between the components can be tolerated. To do this requires that designers make sure each of their combinatorial components is modified so that it becomes sequential. in essence, infer a register on the output. Finally, high fan-out secondary control signals should be registered, and as we will find out later, it is important that you are familiar with all the control signals you have associated with your design. But since synchronous sets, resets, and clock enables are so common, you should always make sure that their source is registered. This helps assure that the long net delay can be tolerated and meet timing. Note that this is especially important for synchronous sets and resets because these paths are automatically covered by the period timing constraint associated with the Xilinx implementation tools. The problem with a high fan-out secondary control signal is that there are limited global routing resources inside of your FPGA. Sometimes you can route your highest fan-out control signals on low skew routing resources that are primarily designed for routing high-speed clocks, but since these routing resources are usually at a premium, most customers have some control signals that they must route on general interconnect. Now, this can be compounded by adding LUTs in series to decode the control signal, and suddenly this control signal becomes timing critical. So we recommend that you always consider coding to infer a register on any high fan-out secondary control signals. As we can see with the code in example A here, the decoded logic not only has a LUT as part of the path, but it also creates a high fan-out net delay that forces these paths to become timing critical. Code B resolves the issue by adding a register after the control signal has been decoded, so the routing delay to the LUT and the LUT delay are cut off by the reg enable register. This assures that the only delay between these two registers is just the high fan-out net delay, which can now be tolerated. An added benefit is that the period constraint will automatically constrain the paths between these flip-flops. A significant caveat to pipelining is the coding for the additional registers. In this case, the high fan-out net isn't too difficult to code for, but the source logic driving data in now needs an additional register. Otherwise, the data would be out of sync. We can't delay the control signal without similarly delaying the data by a clock edge. Since this must be built into the HDL code, it is very important that you keep in mind from the beginning that these kinds of paths are probably going to need this added register. Otherwise, you may be rebuilding your design sooner than you might like. So now we have an example of how to pipeline a high fan-out secondary control signal. In this example, code A has a switch and enable signal inputs. In code B, we have added a separate if-then statement to generate a signal reg_enable. Reg enable is used to enable the data transfer rather than switch and enable being used in the first example. And since this is contained in a register process, this code will infer a register on that clock enable. This implementation will use one additional extra register, but the high fan-out net can now be tolerated. Small price to pay for high performance on a high fan-out net. Likewise, this kind of code can be used to add a register to a synchronous set or reset. So don't be reluctant to use this. In fact, many of our best designers do use this technique. Likewise, here is the same functionality built into a VHDL example. The key is to have a separate if-then statement to build the enable signal. Now let's go ahead and wrap up this module with a brief summary. Well, we try to provide a detailed summary of all the coding tips we provided in this module. First of all, when coding a state machine, separate the next state logic from the state machine output equations. This will, in essence, add a pipeline stage and improve the speed, as well as simplify the number of inputs to the lookup tables associated with the state machine. So this will be a very good enhancement to improve the speed of your state machine. Evaluate whether you need to use binary, one-hot gray, or Johnson encoding for your state machine. And the key thing here is we want designers to spend the time to design properly. Don't just trust your synthesis tool and then it may be choosing the right or wrong encoding technique for you. The only way you're going to find this out is by using enumerated types and then testing each of these out. And again, this result will vary based upon the size as well as the complexity of the state machine. Lastly, we talked about the benefits of pipelining, and we talked about the most common ways in which designers are pipelining their designs. And even in this day of the 6-input lookup table, the newest devices, this is still one of those things that designers are going to be doing. So make sure you take the time to evaluate whether your design needs to be pipelined more. There are some very useful resources available to you on support.xilinx.com. The Synthesis and Simulation Design Guide discusses some of the same topics we covered here. The XST User Guide is very helpful for example inferences of architectural resources. This is often what is most helpful to customers. So I would strongly encourage you to check both of these documents out. Note that all the coding techniques we have shown you here apply to XST. These same coding techniques often apply to other synthesis tools as well. But if you want coding styles and attributes for another vendor's synthesis tool, you'll have to go to their website to learn more about that tool. We also want to encourage you to improve your skills as a designer through our REL databank. Just like you found with this REL, you go to our customer education webpage and you can scroll through a library of different recorded e-learnings to learn more. Learn about different course offerings as well and see what's new with customer education. But whatever you do, please take a second and let us know what you thought of this REL. Just click on the icon at the end of the REL and tell us what you thought of it. And likewise, if you enjoyed it, give us some ideas about other topics that you might like to see us produce. Again, my name is Frank Nelson. You've been listening to the Basic HDL Coding Techniques Part 2 Recorded e-Learning. Thanks for your listening, and thanks for your attention, and thanks for your business.